Okay, let's dive in. So you sent over these really interesting excerpts from a textbook chapter.
That's right. It gets right down to the fundamentals of weather and climate.
Yeah.
Really foundational stuff.
Absolutely, gets right into the weeds, you know? So our mission here, our deep dive, is really to unpack all that,
Mhm.
understand those core differences, what actually makes up our weather, and how we measure it all.
Basically building that solid base for understanding the air around us.
Exactly. And why does it even matter? I mean, the source makes it pretty clear, doesn't it? This stuff affects everything.
Oh, profoundly. It's not just, should I wear a coat today?
Yeah.
It's food, travel, how we live.
Yeah, the source goes into global food supply, building styles, trade routes, even touches on health and, well, other observed human differences.
Which we should probably stress we're just relaying what the source material states on those points.
Right, exactly. Reporting impartially on the source's content. It's a huge topic, but this chapter really nails the basics. So where do we start?
Well, the absolute first thing the text tackles is that crucial difference between weather and climate.
Ah, yes. People mix those up all the time, don't they?
Constantly.
Uh,
But scientifically, they're quite distinct, studied by different fields, too.
Meteorology for weather, climatology for climate.
You got it. And the main difference really comes down to scale, time and space scale.
Okay, so let's focus on weather first. What's the textbook definition there?
Weather is defined as the state of the atmosphere at a specific place and a specific time.
So, like right here, right now, it feels warm or looks like rain. That's weather.
Exactly. A sunny afternoon, a cold morning, a rainy day, that's all weather. And the key thing the source points out is that it's not static,
No, definitely not. It can change fast.
really fast, haphazardly even. The text gives that example of a sunny morning turning rainy just a few miles away, or later the same day. That's typical weather behavior.
That sort of immediate, localized, sometimes unpredictable change.
That's the essence of weather, what's happening right now or very nearby.
Okay, so if weather's the snapshot, climate is the bigger picture.
Precisely. Climate is the average picture, taken over a long time. The text defines it as the average atmospheric conditions of an area over a considerable period.
And it specifies that period, doesn't it?
It does, typically a minimum of 35 years.
35 years. That's a lot of data collecting.
It really is. It involves systematic observation, day in, day out, recording rainfall, temperature, humidity, pressure, wind, sun, clouds, all of it.
And then processing all that data for decades before you can even start talking about averages and climate patterns.
Exactly. It's a long-term, meticulous process to arrive at what we call climate.
So using your analogy from before, weather's what you wear today, climate is your whole wardrobe built up over decades.
That's a great way to put it. And this difference in time scale means a huge difference in variability.
Right, weather can be all over the place day to day.
Hugely variable. Location to location, too. Climate smooths all that out. It describes the pattern, the typical rains, the average conditions based on those 35-plus years of data.
The source had that great example comparing Great Britain and Egypt.
Yeah, that really illustrates the point. In Britain, the weather is famously changeable. Sunny one minute, pouring the next.
So people talk about it all the time because it's so unpredictable in the short term.
Exactly. It's a constant conversation starter. But in Egypt, the climate, the text says, is so consistently hot and dry.
Yeah, that people don't really talk about the daily weather.
Right, because the climate is the dominant condition. The long-term pattern is so stable, the daily variations aren't as noteworthy for general conversation. It's the climate that matters there.
That's a brilliant contrast. Weather's the event, climate's the underlying expectation or lack of dramatic change.
Perfectly put. Snapshot versus the long-term statistical picture.
Okay, got that distinction loud and clear. So why is this understanding so important? The source really emphasizes the practical side.
Absolutely. It says the influence is deep, affecting almost everything we do.
Like what? Give us some examples from the text.
Well, food, for starters. Climate determines what crops can grow, where the temperature, the rainfall patterns.
And then the daily weather forecast helps farmers know when to plant or irrigate or protect against frost.
Exactly. Then there's just basic living, what clothes we wear, obviously, but also how we design our houses.
Right, like steep roofs for snow or building materials suited for heat or cold.
Our work schedules, our daily routines can be shaped by climate.
And the text also brings up those perhaps more controversial points about potential links to things like mental state, physical traits.
Yes, it suggests connections based on long-term environmental conditions. And again, we're just reporting what the source itself observes or suggests.
Understood. Impartial reporting. Beyond the personal, though, it highlights impacts on big economic sectors. Agriculture, obviously huge.
Fundamental. Temperature, rain,
Hmm.
they control growth. But humidity, too, affects pests, fungal diseases.
So forecasts help with immediate actions like spraying, but climate knowledge tells you if it's even worth planting that crop there in the first place.
Precisely. And transport is another big one.
Oh, yeah. Flying, shipping.
Absolutely dependent on weather. Storms, fog, wind, huge factors for safety at sea. Air travel needs detailed info on winds aloft, visibility, clouds, turbulence.
Even on land, snow, ice, floods can shut things down.
And the text makes that neat point about historical trade routes, often following predictable wind patterns, like the trade winds. Shows how long climate knowledge has mattered.
That's a great historical link. It also mentions health impacts.
It does. It makes specific observations suggesting higher death rates in humid tropics versus dry deserts.
Attributing it to easier germ transmission in warm, damp conditions.
That's the reasoning presented in the text, yes, compared to high heat but low humidity in deserts. It also mentions mountain air being healthy. Again, reporting the source's claims here.
Okay, so these wide-ranging impacts really underscore why we need systems to track all this.
Definitely. And the source mentions the global network, weather bureaus, met stations, all collecting data.
Plus satellites now, feeding into everything.
All gathering that raw data that meteorologists then turn into the forecasts we use every day.
But the text also says, you don't have to be a pro-meteorologist to get a sense of things.
Right. Experienced local observers can pick up signs. A falling barometer may be hinting at rain, the feel of the wind changing, certain cloud types.
Just looking up can tell you a lot about right now.
Often it can. But for critical stuff, farmers needing frost warnings, sailors needing storm alerts, that's where the professional services are vital.
So it spans from basic observation to complex global science, all impacting daily life.
It really shows how tied we are to the atmosphere, from the mundane to the critical.
Okay, so we've got weather versus climate and why they matter. Now for the building blocks, the actual elements and how we measure them based on the source.
Right, the ingredients. The text lists 7 main ones: precipitation, pressure, temperature, humidity, wind, sunshine, and clouds, plus visibility.
Let's tackle them one by one. Precipitation first. Seems like a good place to start.
Sounds good. Precipitation is basically any water falling from the sky. Rain, snow, sleet, hail, it's all precipitation.
And we measure it with a rain gauge. Figure 96 in the text shows one.
Yes, the standard type described has a copper cylinder with a funnel on top. The funnel catches the rain over a known area.
And directs it into a smaller container inside.
Exactly, usually a narrower copper can or a glass bottle. This does 2 things. Protects the collected water from evaporating, which the funnel's small opening also helps with.
And it magnifies the measurement, right?
Precisely. Because the funnel's collection area is much larger than the cross-section of the measuring cylinder you pour it into later, even a small amount of rain makes a noticeable depth in the narrow cylinder. Makes for accurate readings.
Clever. But where you put the gauge is critical.
Absolutely crucial. The text stresses open ground, away from buildings, trees, anything that could block rain or cause splashes into the gauge. Needs to be firmly fixed, too.
Okay, so you collect the rain. How do you read the amount?
You take the inner container out, carefully pour the water into a special graduated measuring cylinder. This cylinder is calibrated to match the funnel's area.
So the markings on the cylinder directly read rainfall depth.
Yes. If the funnel area is, say, 100 times the area of the measuring cylinder, then 1 inch of water in the cylinder represents 0.01 inches of actual rainfall.
Wow, very precise. The text mentions accuracy down to 0.0005 inches.
It does, and you have to read it carefully at eye level to avoid parallax error. Looking down or up at the water level skews the reading.
And what counts as official rainfall? Is there a threshold?
Yes, for a rain day to be recorded, the standard mentioned is 0.01 inch or more collected over 24 hours. Anything less, like that 0.005 inch, is just called a trace.
So measurable precipitation happened, but not enough to count towards the official daily total.
Right, and collecting these daily totals lets you build up monthly and annual totals.
Which then leads back to climate, with the mean annual rainfall.
Exactly. That's the average of those annual totals over that 35-year period, a key climate statistic.
And on maps, we see rainfall shown with isoheights.
Isoheights, yeah. Lines connecting places with the same mean annual rainfall.
The text also showed graphical ways to present the data, a histogram.
Yes, figure 97, the histogram for Kota Kinabalu, clearly shows the average rainfall month by month. You see the wet and dry seasons immediately.
And figure 98, the dispersal diagram for Gibraltar, that looked interesting.
That one's really useful because it shows not just the average monthly rainfall, but also the variability. All those dots represent individual monthly totals over 35 years.
So you can see if a month is reliably wet or if the average hides wild swings from year to year.
Exactly. It gives you a much better sense of the rainfall's consistency, or lack thereof.
Very cool. Okay, let's shift from water falling down to the air itself, pressing down pressure.
Atmospheric pressure, basically the weight of the column of air above you pressing on the Earth's surface.
And it varies.
Oh yeah, changes with time, location, and especially altitude.
The classic instrument is the mercury barometer, right? Torricelli's invention from way back in 1643.
That's the one, shown in figure 99. A glass tube, sealed at the top, filled with mercury, then inverted into a bowl of mercury.
And the mercury falls a bit, leaving a vacuum at the top.
Well, mostly a vacuum, just mercury vapor. It falls until the weight of the mercury column inside the tube perfectly balances the weight of the atmosphere, pushing down on the mercury in the bowl.
So the height of that column is the atmospheric pressure.
Directly measures it. Higher pressure pushes the column up, lower pressure lets it fall.
And the standard units, millimeters, inches, millibars.
All commonly used. Standard sea level pressure is about 760 millimeters or 29.9 inches of mercury. Meteorologists often use millibars. Big 113 millibars is standard sea level.
Yeah.
Nowadays, that's often called hectopascals, HPA, so 1013 HPA. It's about 14.7 pounds per square inch of pressure.
And understanding pressure is key to weather systems.
Absolutely fundamental. Low pressure usually means rising air, clouds, maybe rain or storms. Think cyclones or depressions.
High pressure means sinking air, clear skies, stable weather anticyclones.
Right. And how quickly pressure changes tells you how quickly the weather might change.
Maps show this with isobars, lines of equal pressure.
Yes, just like isohyets for rain. Close isobars mean strong winds. Wide isobars mean light winds. Shows the pressure gradient.
You mentioned pressure changes with altitude, too. It drops as you go higher.
Significantly.
Yeah.
Because there's less air above you, the text gives a rough figure of 3.5 inches of mercury drop for every 3,000 feet you ascend.
Which is how planes can estimate their altitude.
Exactly. They use an altimeter, which is essentially a modified aneroid barometer, calibrated to show height based on the surrounding air pressure.
Ah, the aneroid barometer, figure 100, that's the non-mercury one.
Right. Much more portable. It uses a small, partially evacuated, flexible metal box or cell.
And this box expands or contracts with pressure changes.
Just slightly. But a system of levers amplifies these tiny movements and moves a pointer on a dial.
So, more practical than the mercury one, maybe less accurate.
Generally, yes. More robust, no mercury, great for carrying around or in planes. Maybe not quite as precise as a lab-grade mercury barometer, but perfectly good for most uses. And you can attach a pen to make a barograph.
A barograph.
Yeah, it records the pressure continuously on a chart fixed to a rotating drum, gives you a visual history of pressure changes over time. Really useful.
Okay, two types of barometers, both measuring the weight of the air. Got it. Let's move to temperature.
The degree of hotness or coldness, probably the weather element people notice most directly.
And the source calls it very important, varying hugely.
Absolutely. Time of day, season, location, altitude, even just standing in the sun versus shade makes a difference locally.
Measured with a thermometer, using liquids that expand and contract.
Usually mercury or alcohol. As they warm up, they expand up a narrow tube marked with a scale. As they cool, they contract back down.
Two main scales mentioned, centigrade or Celsius.
Which science mostly uses. Freezing point 0 degrees C, boiling 100 degrees C.
And Fahrenheit, still used in some places. Freezing 32 degrees F, boiling 212 degrees Fahrenheit.
Right. And the text gives those handy conversion formulas.
F equals 1.8 times C plus 32.
That's it. So 20 degrees C becomes 1.8 to 20 plus 32, which is 36 plus 32 equals 68 degrees Fahrenheit.
And C equals F minus 32 divided by 1.8.
Yep. So 36 degrees Aris is 3632. 1.8 is about 2.2 degrees C. The source rounds it to 2 degrees C.
Useful for comparing readings. Now, because temperature varies so much locally, you need a standard way to measure it, right? The Stevenson screen.
Exactly. Figure 101. It's essential for getting reliable, comparable air temperature readings. It shields the thermometers from direct sun, rain, and heat radiating off the ground.
Looks like a white box with slatted sides up on legs.
That's it. White reflects sun. Double roof for insulation. Louvered sides let air flow through freely but keep sun and rain out. Usually mounted 4 feet above grass.
And the door faces away from the sun when you open it, north in the northern hemisphere.
Correct. So you don't get a blast of sunlight hitting the instruments when you take a reading. It ensures you're measuring the actual shade air temperature.
Very clever design. The source also describes maximum and minimum thermometers. Figure 102, what do?
They record the temperature extremes over a period, usually 24 hours. The maximum thermometer is often mercury-based.
How does it record the maximum?
It has a narrow constriction near the bulb. As temperature rises, mercury expands past the constriction. When it cools, the mercury column breaks there, leaving the end of the column indicating the highest temperature reached.
And you reset it by shaking it down.
Usually a flick or swing forces the mercury back through. The minimum thermometer often uses alcohol, which stays liquid at lower temperatures than mercury.
And it has a little marker inside.
Yeah, a small index or dumb ball. As the alcohol contracts with cold, it pulls the index down. When it warms up, the alcohol flows past, leaving the index at the lowest point reached.
So you read the top of the index for the minimum temp?
Well, the end of the index, furthest from the bulb, marks the minimum, and you reset it by tilting the thermometer or using a magnet if the index is magnetic.
Okay. And tracking max and min temps gives you the daily temperature range.
Yes, the diurnal range, the difference between the day's high and low, and comparing the average temp of the hottest and coldest months gives the annual range.
Like that Mukden example in Figure 103, showing a huge annual swing.
Typical for deep continental locations. And temperature maps use isotherms.
Lines of equal temperature, often adjusted to sea level.
Yes, to remove the effect of altitude and compare climate patterns more easily. The text mentions that rough 1 degree aperture drop per 300 feet increase in altitude again here.
Okay, temperature covered. Next, humidity, the air's dampness.
Exactly. The amount of water vapor in the atmosphere. Hugely important for clouds, rain, even how comfortable we feel. Varies a lot too.
The source focuses on relative humidity, RH. Why relative?
Because how much water vapor air can hold depends massively on its temperature. Warm air holds more than cold air, so relative humidity compares the actual amount present to the maximum possible amount at that specific temperature. It's a percentage.
So 50% RH means the air holds half the water vapor it could at that temp.
Precisely. 100% RH means that saturated can't hold anymore. If saturated air cools, water vapor condenses out.
Into dew or fog or clouds. And the temperature where that happens is the dew point.
You got it. High RH means damp air, low RH means dry air, like in deserts.
How's it measured? The hygrometer, specifically the wet and dry bulb thermometer type, Figure 104.
That's the standard instrument, usually kept in the Stevenson screen. 2 identical thermometers side by side.
One dry, one wet.
Right. The dry bulb just measures the air temperature. The wet bulb has its bulb covered in muslin kept moist by a wick dipping into distilled water.
Okay, how does wetting one bulb measure humidity?
It uses evaporation. Water evaporates from the wet muslin, and evaporation takes heat energy from the bulb, cooling it down.
And how much it cools depends on how easily water can evaporate.
Exactly. If the air is very dry, low RH, evaporation is rapid, the wet bulb cools a lot, and its reading will be much lower than the dry bulb.
If the air is already damp, high RH, evaporation is slow, so the wet bulb cools only a little.
Or not at all if the air is saturated, 100% RH. In that case, both thermometers read the same.
So the difference in temperature between the two bulbs tells you the relative humidity.
Precisely. A big difference means low RH. A small difference means high RH. You use the 2 readings with special tables or a calculator to find the exact RH percentage.
That's really clever, using the physics of cooling by evaporation. Okay, next element, wind.
Simple definition. Air in motion. Described by direction and speed.
Direction measured by a wind vane, Figure 105.
The classic rooftop arrow. It pivots freely, and the wind pushes the tail end, making the arrow point into the wind, showing where the wind is coming from.
So a north wind comes from the north? Makes sense. Needs clear sighting, right?
Yeah, high up, away from obstructions. Direction reported using compass points. N, S, E, W, N, E, S, W, etc.
And speed measured by an anemometer, Figure 106. Often looks like spinning cups.
That's the common type. 3 or 4 hemispherical cups catch the wind, making the central spindle rotate. The faster the wind, the faster it spins.
And that rotation is counted somehow.
Yep, linked to a counter or sensor that translates rotations per minute into wind speed, miles per hour, knots, whatever unit is needed. Again, needs good exposure for accuracy.
The text also mentions the Beaufort wind scale, Figure 107. Not an instrument, but a way to estimate speed.
Exactly. Developed by Admiral Beaufort for use at sea observing wave conditions. Now adapted for land, too. It links observable effects, smoke drift, leaves rustling, branches moving, damage to a number scale, 0-12, and corresponding wind speed ranges.
So scale 0 is calm, smoke rises vertically. Scale 7 is a moderate gale, hard to walk. Scale 12 is hurricane devastation.
Right. It's a really practical way to estimate wind strength just by looking around, especially if you don't have an anemometer handy.
Very useful visual scale. Okay, next. Sunshine, how is that measured?
The instrument described measures the duration of bright sunshine. It uses a solid glass sphere,
Like a crystal ball.
sort of, about 4 inches across. It acts as a lens, focusing the sun's rays onto a point.
And that point burns something.
Yes, it burns a track onto a special card held behind the sphere. The card is marked with hours. As the sun moves, the burn mark follows.
So the length of the burnt track equals the hours of bright sunshine.
That's the principle. You measure the track length at the end of the day.
And sunshine duration varies a lot with latitude and season.
Hugely. The source notes it's a bigger focus in temperate latitudes, where it affects growing seasons, than in the tropics, where sunshine is generally strong year-round.
Makes sense. Focus on what varies most. Okay, element 6, clouds.
Visible moisture. Tiny water droplets or ice crystals floating in the air, formed by condensation.
And they tell us a lot about the weather.
A huge amount. Their shape, height, coverage, it all gives clues about moisture, stability, potential rain.
Classified by form, height, and appearance, the source says. Let's go through the types. High clouds first, 20,000, 40,000 feet.
Right, these are icy. Cirrus, thin, wispy, mare's tails, often fair weather. Cirrocumulus CC ripples, mackerel sky. Cirrostratus thin veil often causes halos around the sun or moon.
Medium clouds next, 7,000, 20,000 feet.
Water droplets or mixed ice water. Altocumulus AC, woolly patches, bumpy layers. Altostratus AC, grayish sheet. Sun dimly visible like through ground glass.
And low clouds, below 7,000 feet.
Mostly water droplets. Stratocumulus CT, lumpy layers or rolls. Stratus, St. Flat, gray sheet, like fog that hasn't reached the ground, often brings grizzle. The text calls it a rain cloud if precipitating.
And nimbostratus.
That's the main rain cloud. Darker, thicker stratus, producing continuous rain or snow, low to mid-level.
Finally, the vertically developed ones, cumulus types.
Right, cumulus Q, the puffy cotton wool clouds with flat bases and rounded tops. Fair weather clouds unless they grow.
And if they grow really big,
They've given cumulonimbus, kunai. The massive thunderstorm cloud extends very high, dark base, often an anvil-shaped top, brings thunder, lightning, heavy rain, hail. The thundercloud
recognizing these is key for short-term forecasting.
definitely shows what the atmosphere is doing vertically.
How is cloud cover measured?
In eighths of the sky covered, called octas. 08 is clear, 48 is half covered, 88 is completely overcast.
And maps use symbols for cloud types and cover, and isonephs.
Yes, special codes and symbols on weather maps. Isonephs are lines connecting places with equal cloud cover.
Okay, one last element mentioned, visibility.
Simply how far you can see. Crucial for transport. Affected by things in the air.
Like haze, mist, and fog.
Exactly. Haze is from dry particles, smoke, dust, pollution. Scatters light, reduces visibility, often when humidity is relatively low.
Mist is actual water droplets.
Yes, tiny ones, like a thin cloud at ground level, happens in damp air, higher humidity, reduces visibility more than haze down to about 1,000 meters or so.
And fog is just denser mist.
Much denser. Visibility below 1,000 meters, sometimes much less. A thick ground level cloud. Smog is fog mixed with smoke pollution.
Where does fog typically form?
Hills, valleys where cold air pools over cold seas when warm moist air moves over them. Tends to be denser and lasts longer over land.
So visibility measures air clarity, vital for getting around safely.
Absolutely. Road, sea, air, all heavily impacted.
Right. Well, that's a comprehensive run-through of the elements and how we measure them, straight from the source material. We covered the weather-climate difference, their importance.
And then precipitation, pressure, temperature, humidity, wind, sunshine, clouds, visibility, and the tools we use, the solid foundation.
So bringing it back to you listening.
Yeah.
Why does this all matter? What's the takeaway from this deep dive?
Well, understanding these basics, it changes how you see the weather. You go from just experiencing it to having some idea of why it's happening.
You can read a forecast with more understanding, maybe even start noticing the patterns in your own area.
Exactly. It demystifies the atmosphere a bit, makes you appreciate the complexity and the science behind trying to predict it. You start seeing the data behind the daily experience.
It gives you the language and concepts to connect the dots.
Turns the invisible into something a bit more tangible, more understandable.
Definitely feels like we've built that foundation the source aimed for.
I think so. Cover the key concepts thoroughly.
Okay, so let's leave you with a final thought. We talked about climate being built on decades, at least 35 years, of these daily weather measurements, temperature, rainfall, pressure, all meticulously recorded.
Hmm. That long-term data collection is crucial.
So consider this. That very same detailed, long-term data gathered using the instruments and methods we've just discussed is now the bedrock evidence for understanding large-scale global climate change. Does getting into the nitty-gritty of measuring today's temperature or rainfall change how you think about that huge, multi-decade picture of our changing climate? Something to chew on.